Welcome to this lecture series in coordinate geometry. In this lecture, we look at the notion of concurrency. And again, all we need to know is basically what is meant by the equation of a line. So let us continue. Here are some problems for practice. And now let us get started. So let us define concurrency. This is, of course, a notion of plane geometry or just Euclidean geometry. So suppose we have three lines, and these three lines, let's say, are on the plane, although you can define this concept of concurrency even for 3 dimensions, but let us restrict our attention just to the plane. So suppose we have 3 lines in the plane, then we say that they are concurrent if there is a point lying on all 3 of them. There is a point which lies on all 3 of them. Okay, that's the definition. Here, under this definition, even if L1 were equal to L2 were equal to L3, even those 3 would be counted as concurrent lines. But of course, when we are talking about concurrency, that is not of interest. That is some sort of a degenerate case. And let's say L1 were equal to L2, but L3 was some other line. Even then, concurrency might happen. But the interesting cases are things like these. We have 3 lines, no 2 of them are parallel, and there is a point through which all 3 of them pass. So this is an example of concurrency. While here we have 3 lines, but there is no point which lies on all 3 of them. This point lies only on L1 and L2. This lies only on L3 and L1. And this one lies only on L2 and L3. And there is no point which lies on all 3 of them. So these 3 lines are not concurrent. Okay. Another very interesting example is that medians of a triangle are concurrent. You take any triangle, you draw the 3 medians. Recall, a median is a line passing through a vertex and through the midpoint of the opposite side. So you draw the 3 medians, you will find that always they will be concurrent. There will be a common point through which all of them pass, and this point is called the centroid of the triangle. Okay. And in fact, we will hint at a proof of this using coordinate geometry in this lecture. All right. So what we are interested in is an algebraic criterion to detect concurrency. The notion of concurrency is, of course, just a geometric one, but if you want to study it algebraically, then what we would want is, suppose we are given 3 lines and we have been given their equations, can we, in terms of the equations or the coefficients that appear here, can we write down an algebraic condition which detects concurrency? And indeed we can. So suppose we have 3 lines, L1, L2, L3, whose equations are these, and inherent in this expression is that not both of A1 and B1 are 0. Similarly for A2 and B2, and similarly for A3 and B3. So that these are indeed lines. Okay, and assume that these lines are not parallel. So if all 3 of them were parallel, then that's sort of a degenerate case. We will not be talking about that case. In that case, anyway, it's very easy to check for concurrency and whatnot. So assume the lines are not parallel. Then the 3 lines are concurrent if and only if this horrible expression is 0, which is a purely algebraic expression coming from the coefficients, the 9 coefficients that we see. All right, so that is a fact. We will prove it, but the proof we will give will borrow from things outside the scope of what we have discussed so far. We will borrow from 3D geometry. We will use notions of vectors and box product and so on. Even if you don't know about those things, I would encourage you to look at the proof and try to follow as much as you can. the main intuitive ideas should be available to you regardless. Before we continue to the proof, let me just comment that this expression here is actually the determinant of the following matrix. So you make this matrix and take the determinant. That is the above expression. If you don't know anything about determinants, ignore this. Okay, so let's proceed to the proof. All right, so first we will assume that the three lines are concurrent. That is, we will derive the truth of the algebraic expression that was written, and then the reverse direction we will say something about. So first we will assume that the three lines are concurrent and arrive at that algebraic expression. All right, so if the lines are concurrent, then there is a point in the plane which lies on all the three lines. Which means that this is 0, and similarly for the other two lines. Right? All we have done is, if you use the fact that this lies on L1, you get this equation. This lies on L2, you get that equation. And this lies on L3, you get this equation. Okay, so we have just used what is meant by concurrency. All right. Now we will move to 3 dimensions. The picture here is drawn. We will move to 3 dimensions, and this is where we move out of our study of the coordinate plane. We will borrow from 3D geometry concepts. All right, so consider the following vector. What is this vector? This vector is the vector whose tail is that point. So this plane here, this is the horizontal plane, meaning the plane parallel to the xy plane, passing through this point 0, 0, 1. And this vector is the one whose tail is at this point. Maybe I will rewrite it. Right? So we have that vector, and now in terms of the vector language, what does the first equation read? So we will define 3 more vectors. So let's call this one, we will call this one as x. So say the vector x is this guy, and v1 is, we define that as this one. So of course, I mean the vector whose tail is this point. In high school, we think of vectors as arrows with a tail and a head. When I write that v1 is this vector, I just mean the vector whose tail is here and whose head, sorry, not the tail. The head is here. So whenever I was calling tail, actually I meant head. So the vector whose head is at this point and tail is at the origin. So something like, I don't know, something like that somewhere, depending on what the values of a1, b1 and c1 are. So that is v1. Similarly, we have v2 and we have v3. Okay, we have these 3 vectors, and in the coordinate language, or sorry, in the vector language, the first equation reads what? It just reads that the dot product of v1 and x is 0. The second one reads this dot product is 0. And the third one is this dot product is 0. Now, if you haven't come across the notion of dot products, then this proof will be lost on you. But what can I do? You can revisit it when you learn about dot products. So we have these 3 dot products are 0, which means what? Which means v1 is perpendicular to this, v2 is perpendicular to this, and v3 is perpendicular to that. So all the 3 vectors are perpendicular to this guy. Now this guy is of course a non-zero vector because its head is certainly not on the origin. This is certainly not the origin. So all the three vectors v1, v2, v3 are perpendicular to a given non-zero vector, and hence the three of them lie on a single plane. There is a single plane which contains all the three vectors. So all I'm using is the fact that the set of all the vectors perpendicular to a given non-zero vector form a plane, and therefore these three vectors lie on a plane. Now if they lie on a plane, then therefore the volume of the parallelepiped spanned by the three vectors is 0, which means that the box product of these three vectors is 0. The box product precisely measures the volume of the parallelepiped, and therefore this thing is 0. I don't know the notation of the box product, I have forgotten it, but I think it is this. So this is 0, and if you just use the formula for the box product, you will get this algebraic expression, this thing. So that proves if the lines are concurrent, then the algebraic expression that we saw is indeed 0. And now if the algebraic expression that we saw is 0, you want to prove the three lines are concurrent, you would kind of just reverse this reasoning, but at some point you will be using the assumption that the lines are not parallel. So the reverse direction is an exercise, but you have to be mindful that at some point you will be using that assumption. Without that assumption, you won't be able to prove it. Okay, so that's a very nice proof. And let me comment on how to use and what is the use of concurrency to establish geometric facts. So here is the first one. Let's try to see why the medians of a triangle are concurrent. Of course, you can write down beautiful geometric proofs of it, but here is the kind of mindless mindless coordinate geometric approach. So you have this triangle ABC, and you have the three medians. Let's try to write down the equation of this median. So if we could figure out the coordinates of the midpoint, which is D, the midpoint of BC, which is D, then we know the coordinates of this and the coordinates of that, and then we can write down the equation of this line. But since D is the midpoint of these two, the coordinates of D are those. And now it's just a line passing through these 2 points. And if you just make the calculation, this is the equation of that line. Similarly, you write the equation of this guy and write the equation of that guy. And then you will have these three humongous equations. And just use the formula for concurrency, you will have established that the three medians are indeed concurrent. So it is a long calculation, but it is not requiring any intellectual effort. So that's one example, one application. And this is another application. The altitudes of a triangle are concurrent. So here again, you can do the same thing. You can take the coordinates of A as x1, y1, this as x2, y2, and that as x3, y3. And then you know the equation of this line, and then this is perpendicular to that line, so you know its slope, but you also know a point through which it passes, so you can write the equation of this altitude. And similarly, you can write the equation of the other two altitudes, and then you just use the theorem about concurrency and establish that the three altitudes are concurrent. But here you can save some of your computation by choosing the coordinate axes properly. So you can choose the origin here. You can choose this as the x-axis and that as the y-axis. So therefore, it will be easy to write down the equation of this altitude. This is just x equals 0. And then you can struggle with the equation of the other two altitudes, and that will save some computation. So that's the only reason I wanted to discuss this. All these concurrency things will be given as exercises later. But I just wanted to make a point here that sometimes choosing the coordinate axis properly or rightly saves a lot of computation. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.